So next we talk about artificial neurons, which are the basic computational units of artificial neural networks. And these are, like we said, very crudely based on real life biological neurons. The history of artificial neural networks and artificial neurons are at least 70, 80 years old now. In the 1940s, during the Second World War, in fact, McCulloch and Pitts worked on creating one of the first simulations, computer simulations of artificial neural networks while modeling neurons in simple ways. And in the 1950s, Rosenblatt built a machine called the perceptron, real hardware, which implemented a simple neural network for classification. In fact, with sort of close similarities to logistic regression that we saw before. This is called a perceptron. There's some small technical differences. Okay, so that history is rather old. Um, okay, so what do simple computational or artificial neurons look like? Um, Say we have m scalar inputs, x1 till xm. You construct a weighted sum of these inputs. Z equals W1 x1, W2 x2, etc., with summing over all these things. This is kind of like summing over inputs from different neurons and giving each one a different weight. Okay, the weights can be positive or negative to indicate excitatory or inhibitory neurons. Okay, okay, so that's Z, and then we say if Z is greater than some threshold, we say Y equals 1. If Z is less than some threshold, we say Y equals 0, where Y is the output of the neuron. The X's are the inputs, and Y is the output. Okay, there's one scalar output, and there are M scalar inputs. And you would represent this in this manner: inputs, neuron, output. And your Z, like we said, is just a weighted sum of all the inputs, and then Y is some function of the Z. And this function, h of Z, is this threshold function. It's 0 until you cross the threshold, and then it's 1. Okay, so uh, neurons are just this incredibly simple things, at least these artificial neurons. It's just a function. It's just a simple function, h of x or something. Actually, h of z, which is some function of x. Okay, you have some y equals some function of x, and what is that function of x? It's the threshold function of a linear function of x. Okay, very simple. Now, an alternative equivalent representation of what we just described is as follows. Instead of having this threshold be some quantity and this h depend on the threshold, what they do is have z also have a constant term, w naught. Okay, so we say z equals w naught plus w1 blah blah blah, and then h is defined with 0 as a threshold. Okay, so h of z is if z is less than 0, you get a 0. If z is greater than 0, you get a 1. And so that's z, y equals h of z is defined in this manner. Okay, 1 if z is greater than 0, 0 if z is less than 0. Okay. So what we've done essentially is that taken this threshold and stuck that into this linear expression. So the threshold is actually minus w naught. Okay, so this whole thing will exceed 0 when this part will exceed minus w naught. So minus w naught is the threshold for this particular expression. Okay, so that's a very simple expression. The weights wi that pre-multiply the xi are called the weights. And then w naught, the constant term, is called bias. This is just neural network lingo, I suppose. Um, Sounds good. So effectively, what we have is this function of x, y equals h of w naught plus summation wyxi. So we have a linear function of the inputs, and then we have h, which is a nonlinear function of a linear function of the inputs. H is called an activation function, again in the neural network world. So effectively, what we have is a nonlinear function of x. Linear plus something nonlinear gives you something nonlinear. Okay. I described a version of the neuron with this very particular activation function called the threshold activation function. Okay. But people have used a variety of activation functions in the recent past for neural networks. The threshold activation function maybe was the first historically, and then the logistic or sigmoid activation function was the next one that was used historically, which was meant to approximate the threshold activation function with something smoother so that you can differentiate and so on. Okay. Um, And then more recently, just in the last 10, 15 years, people started using something that is different from these two activation functions, which I think the name of this object is unfortunate, but it's called a rectified linear unit. Um, so it's 0 for z less than 0, and it's equal to z for z greater than 0. I should say um, this should say h of z equals z for z greater than or equal to 0. Okay, h of z equals z, so it's equal to z for z greater than 0. Okay, I'll post a correction on my notes that I post. This by far is the most commonly used activation function in modern neural network work on the computer science side. Okay, it doesn't necessarily have a biological analog, or at least an exact biological analog. There are some um, versions that one can imagine where a neuron fires with greater frequency if you increase some input to it. But in any case, this is what we use in modern computational neural networks, where h of z equals z when z is greater than 0, h of z is equal to 0 when z is less than 0. Um, I used to call this the positive part function. It's called the rectified linear unit because you just have a line here. That would be a purely linear function. Rectified meaning you just let through the positive part of the output. You kill the negative part, you let through the positive part, and which is something people do when you convert AC to DC in electrical engineering. That's called rectification, letting through only the positive part of a signal. Um, and I sometimes like to call it the positive part function, which is what it does. So if you give it an input, if it's a positive number, the output is the same positive number. If it's a negative number, you get a 0. Okay, so it gives you the positive part of the input. People also use something called a leaky ReLU. This is contracted to this word ReLU, ReLU activation functions. Um, and yeah, so this one essentially has h of z equals z when z is greater than 0. And h of z equals um, epsilon times z, where epsilon is a small negative number, small slope for z less than 0. Okay, this people had some excitement about this activation function a few years ago, but overall people have settled on using this activation function for pretty much most modern neural networks because they seem to work best. We shall see later on why that might be. Okay, so that's about a single neuron. Okay, it's very simple. It's a linear function. It's a linear function times a nonlinearity, or a nonlinearity acting upon a linear function, and the nonlinearity can be one of these things. Maybe other things as well. Okay. Now we can put together these neurons in some kind of a network to create more complex functions, essentially. Okay. So a neuron is just a name for, in our case, a particular simple function. Right? It's just like sine, cosine, neuron. Okay. Nothing more, nothing less. Okay. So now let's construct the simplest neural network consisting of these kinds of neurons. And the simplest neural network consisting of these neurons is actually a single neuron. You can imagine a single layer feed-forward neural network where actually consisting of a single neuron, where you have these M inputs and then one neuron, let's say, and then one output. Like we said, this is the function that takes these inputs to the outputs. This one layer is called the output layer, just a name. And it turns out that actually if H is the sigmoidal or the logistic activation, this thing, this relationship between the output and the input is exactly the same as what we used for logistic regression. Okay, so in logistic regression, specifically binary classification, logistic regression, what did we do? We took the inputs, namely the pixel values, let's say for input, MNIST. We computed a linear expression of it, which looked like this, z equals blah. And then we just apply the logistic function, h, of that linear function, and that's your output, okay? So a single neuron is basically like the logistic regression functional relation, okay? Of course, a single layer feed-forward neural network can also have multiple neurons where these things, these inputs also have go to another neuron, and so on. And each of the neurons will give you a different output if the weights are different, okay? So this is a single layer neural network with just one output, but you can imagine versions with many outputs. It's called feed-forward neural networks because the signals keep going forward along the network feed-forward. There's a class of neural network called recurrent neural networks where the output of, let's say, a bunch of layers of the neural network gets sort of wrapped around and made to be the input of the neural network back again. So there is sort of feedback connections. And those are called recurrent neural networks, which we will discuss later on in the course, okay? But this thing where things just move forward is called the feed-forward neural network. And really, it's just a function, okay? Here we have a two-layer feed-forward network, again, with just one output. Of course, you can have many outputs, and that would also be a two-layer feed-forward network. Okay, so we have a whole bunch of inputs. Each of these inputs potentially go to a whole bunch of neurons. And then this whole bunch of neurons, the outputs of those things go to perhaps another whole bunch of neurons which provide the outputs, okay? So we have the output layer where you can have multiple neurons. In this case, I've just drawn one. And then you have what's called the hidden layer, which is in between the output layer and the input layer. And then we have the input layer. So superficially, it looks like three layers, but the input layer is not really consisting of neurons. It's just inputs. So these two are the neuronal layers. So this is called a two-layer feed-forward network, okay? Of course, each neuron will have its own set of WI, the weights and biases. And what we do is essentially try to find these weights and biases in a manner that best fit data. Like if we have output and inputs, we tune all these parameters, WI, in a manner that the output is well predicted from the inputs in the data. Like I said, there can be more than one output, in which case you would just have multiple output neurons here. Okay. Very often, a network like this is actually depicted in this manner, where the input layer also has circles around it. But we don't necessarily count these things as neurons because all they are communicating um, the signal forward to the hidden layer without any transformation. So this is just input layer, which is not counted as a layer, and then the hidden layer and the output layer are the two layers that consist this neural network. Okay. Of course, we can have multi-layer networks, which usually means more than one hidden layer. We have an input layer, we have a whole bunch of hidden layers, we have an output layer. Okay. And these layers are connected in some manner. You can have what's called fully connected connections. Fully connected meaning all neurons here are connected to all neurons here. All neurons here are connected to all neurons here, so that all possible pairs of connections are there. That would be called a fully connected sort of connection. You can have other kinds of sparsely connected sort of connections as well. And that's something that we will look at later on. Okay. Just some more terminology here. Like we said, input layer is not counted as one of the official layers. And then the number of other layers is called the depth of the network. I should say network depth here. And then each layer will have so many neurons. The number of neurons in a layer is called the width of that layer. Okay, and the width of the layers can be different. This can have 3 neurons, this can have 20 neurons, this can have 200 neurons. The next one can have 3 neurons. Next one can have 5 neurons. All that's totally fine. Okay. The number of neurons in each layer need not be the same, and the number of layers itself, the depth of the network, can depend on the application. So all in all, well, the inputs and the outputs could be continuous or discrete, namely sort of categories, or it could be continuous variables. But all said and done, what this framework provides is just a big giant function, right? Which takes the inputs through some complicated set of transformations through these things that we call neurons to some outputs y. Okay, that's all it is. And what we mean by learning in this context of neural networks is actually solving for the unknowns, W0, W1, Wn for each neuron. So these numbers will be different for each neurons, such that we approximate or fit the neural network to some data as well as possible. Okay, so for instance, we might minimize the mean squared error, in which case we would just find the minimum over all W0, W1, etc. for all neurons. And then we minimize summation over all data points, outputs minus some function of the inputs and all the weights and biases squared. And this function is basically our neural network, right? The neural network is a function, and this is the function. It's a function that depends on all the inputs and all the weights and biases for all the neurons, okay? And determining these given this and this by minimizing this whole thing is what supervised learning in neural networks is all about. So it's just an optimization problem. It's just a big optimization problem. And what people call deep learning is just having more layers. Usually more than, I don't know, 5 or 6 layers would be called deep learning. Sometimes maybe fewer, but sometimes maybe more. I think people choose what they want to call deep and deep learning. Depends on what they want to do, I suppose. Okay, so anyway, so it's just a big optimization problem, trying to minimize, say, the mean squared error or potentially some other loss function like the logistic loss function or cross entropy loss function that we've used for classification problems. So in fact, those two are the big two loss functions. We would either minimize mean squared error or we would minimize the softmax or cross entropy or logistic class function that we've used in binary or multi-class logistic regression. Those two will be the two main types of loss functions that people use, even in neural networks. So that's why we spent quite a bit of time building up expertise in mean square error minimization for least squares regression, and then logistic regression or classification, right? Because that's what people use in neural networks as well. Okay, so how do you solve this optimization problem? We usually just use stochastic gradient descent, like we've described in the last couple of lectures, or we use small variants of the algorithm. It's actually more traditional to use a small variant of the stochastic gradient descent algorithm, but it's called SGD, stochastic gradient descent with momentum. I'll briefly discuss that in the next lecture, and that's what people use often, or other modern variants of it. Okay, so let me stop this video there.